All right, hi everybody. Welcome to another set of notes. This is unit number 2, our very first presentation in this unit. And this week we're going to be talking about the different types of forces that we see in this world. All right, so as we get our digital notes notebook open, just a reminder that we need to make sure that we are typing up everything that is typed up. If I write on the document or draw anything on it, that is something that should be included into your digital notebook. So please make sure that if there's any drawings or pictures, please screenshot those into your notebook. Okay, so let's get started. Okay, so a force is, by vocabulary words, it's a push or a pull that changes an object's motion. In other words, it creates acceleration, right? Whether that means it can slow an object down or speed an object down, some kind of acceleration takes place whenever there is a force, right? Force has two things. It has direction, so it tells that force has to go in a certain direction, and it also has a certain strength, right? And that strength is actually measured in newtons, right? That's something that we'll be discussing a little bit more in class, and we'll have a new tool that I'll be showing you, which is called the spring scale, right? And forces can actually happen through contact or no contact. Now, most of the forces that we'll be going over, they all have some kind of contact that happens. In other words, two objects actually have to be touching each other in order for a force to happen. But there are ones where two objects do not have to be touching each other in order for a force to occur. All right, so I'm going to go through about 8 different types of forces that you see in the world every single day, pretty much. All right, some are you'll see probably more than others. One being applied force, which is probably one of the more that you'll see in your overall. And a description of that is just any person or an object that pushes or pulls on another object, right? And I have 2 examples, right? So anytime that like you literally pick up something or you push something across a room, like this person pushing a box, that is an applied force, right? It can also be 2 objects that are pushing or pulling. So a car accident, right? When another car runs into another car, right? Isn't that just a car pushing another car? It just so happens to create damage. But both of those are considered applied forces. All right, our second type of force that we'll be discussing and doing some work with, and this one will also be towards when we talk about space as well, which is gravity, right? Gravity is what we considered a non-contact force. We always think of forces or gravity as, hey, something, if I drop something, it falls to the ground, right? And so why is that? Well, the term technically is that gravity it's a force of attraction between 2 objects, right? And what that really means is that any 2 objects that have mass are going to be attracted to one another. So in other words, what that means is, right, I have this computer in front of me right now, and what that really means, what gravity means is we both have gravity. And a computer technically wants to be attracted towards me. Now, why is it that we don't see that here on Earth? And that's because the Earth is so massive. And so instead of the attraction of the computer wanting to come to me, it's more attracted to the Earth. So it's going to want to go downwards, right? So if I put a ball in front of me, or like an apple, let's say, right, in my picture right here, if I put that apple in front of me, it's actually attracted to me. It has gravity towards me. However, what does it do? It actually falls to the ground. Well, why? It's because it's going to be more attracted to the Earth because the Earth is so much more massive than I am. Right? It's kind of an interesting thing, but here on Earth, we always just see gravity going in one direction, which is downwards, right? But in actuality, if you were going into space where there's not much, where there's not really gravity, you're going to see some interesting things. Unfortunately, we can't go out into space and do all these little cool things. So obviously, when you see like Wile E. Coyote, right, falling off a cliff, he's going to go downwards because that's what we see here, right? And then the last thing that I want to talk about with gravity is weight is the measurement of gravity, right? So what do we use? We usually use a weight scale, right? So when you see Garfield right here, when he steps on it, you'll see that this little needle moves. And that's how we measure actually gravity here on Earth. And so we use kind of like pounds in that case, but in reality, we should be using newtons um, to do that. But that's gravity. We'll talk a little bit more about gravity because gravity, the force of gravity, is such um, a unique kind of force that we talk about because it's probably the only non-contact force that we are discussing here amongst the 8. All right, so our next force is normal force. Again, this is another one that we see a lot of. We just don't really think about it. But basically, a normal force is when a surface pushes against an object so it actually doesn't fall through it. A big example is your table, right? You probably set things on your table, right? Well, why is it that the object doesn't fall right through the table? It's because the table is pushing up against that object so it stays right there, right? So that's what we see often, right? A lot of times we don't even think about it, but that's kind of what happens because gravity is always around us. So there has to be a lot of normal forces to make sure that those objects don't fall right through objects, right? And so the normal force, depending on the angle of the surface depends on which direction the normal force is going to go, and it's always going to go perpendicular to the surface. So if you look at these pictures right here, right? If you think of this black line as a table, right? It's always going to be perpendicular. So it's going to create that 90-degree angles to the surface. So if I turn it kind of like a little bit on an angle, that normal force is going to go a little bit in a slightly different direction, all right, as if you were saying right here. But it's just a surface pushing against an object, so it doesn't go right through it. All right, so buoyant force is our next force that we'll be talking about. And basically, buoyant force is when you put an object in a liquid, right? Every object, right, or every liquid pushes up on the object. And if you get something that really, really floats well, like this ball right here, you get this cool thing. And I'm sure everybody's done this in a pool, right? You get a beach volleyball or you get like one of those basketballs and you put it underwater and you let it go and it flies into your face, right? Well, that's because the buoyant force, right? The liquid is pushing up on it. And so if you get something really, really buoyant, it can actually jump out of the water, right? So that works for things that float. You can also, if you look at the guy right here that is kind of doing some weights, it also works for things that sink too. It's not just buoyant force, it's only for things that float. If you ever been in a pool before and you try to lift something that seems really, really heavy, but then all of a sudden you try to lift it underwater, you're like, oh, it's not that heavy. Well, it's because, right, even if you put a 50-pound dumbbell in a pool, well, that 50-pound dumbbell might actually have a buoyant force of 20 pounds. So instead of feeling like 50 pounds, it might feel like 30 pounds underwater. So it feels lighter. So things are going to feel lighter underwater because it's helping you lift it off the ground. So every object has something like that. That's also the reason why if you put an ice cube inside of your water, what happens always, right? The water level goes up. And that's because the water is pushing up against the ice cube. Okay, so that's buoyant force. Next force is tension, right? So basically tension is created when anything is being stretched or elongated, right? So I have two examples here where you use a rubber band and right? Obviously, working with the car project, we have the balloon, right? So, right, the big thing with this one is understanding which direction actually tension force goes. It's actually not us physically stretching it, right? So us physically, like if I look at this one right here, if I use my fingers and I stretch it out, that's not tension. So my tension force is actually not going outwards, right? What's actually happening is that is an applied force, right? Because I am physically moving the rubber band outwards. Tension force is the force that makes the object go back to its original shape. Well, if I let go of that rubber band, well, which direction does the rubber band want to go back, right? And it's going to go back this way, right? It's going to go back inwards. So tension force actually goes usually inwards, right? It's always going in the opposite direction that the applied force, in this case, is going. So tension force is when you were to let it go, what happens? Same thing with a balloon, right? The tension force is not when I blow into the balloon to make it bigger. That's actually me doing that. That's an applied force, right? So the tension force is actually what happens when you stop, right, blowing it up. Well, what happens when you let it go? What does the balloon want to actually do, right? The balloon wants to get back into being smaller. So tension force is always going to go back inward towards itself. So that force of tension is always going back inwards. Even though the object is being stretched, tension force wants to bring it back. That's the reason why, right, if you feel a rubber band, when you pull on it really, really tight, what do you feel? You feel a lot of pressure in your fingers, right? And that's because the rubber band wants to go back into its original shape, so it goes back inwards. So tension force, right, is created when it's stretched, but it really is that force that's going inwards. Opposite of tension force is what we call compression force, right? And that's when something is being, so when an object is getting compressed, right, or it's being pushed to get smaller, right? Well, again, remember, compression force isn't like if you look at the guy who's pushing the spring in, right? Compression force isn't the actual act of squeezing it. That's an applied force. The compression force is the force that makes it want to go back into its original shape. So if I squeeze a spring like that, well, what does a spring want to do once I let go? It's going to want to go back outwards, right? So in this case, compression force is more of an outwards force. It's going to want to get bigger again because it's being smushed, right? So when I draw the compression force, I'm showing it going outwards, right? Not being inwards, because that force going inwards is actually being the applied force. Same thing with the guy who's getting hit with a soccer ball, right? The ball getting smaller or getting squeezed, again, is the applied force because it's the guy's face that's actually squeezing the ball. But what does the ball want to do? Right afterwards, it wants to actually get blown back up. So what is it going to do? The ball is actually going to elongate again. It's going to get bigger because that's the shape that a soccer ball normally is, right? It's a round ball. So it's going to want to push back against the guy's face, and that's the reason why a ball bounces off of something, right? It's because it's pushing off of the other object because of the fact that it wants to get bigger again. So that's compression, which is the exact opposite of tension force. The last two forces I'm going to be talking about is friction and air resistance. And I put them both on the same slide because they're basically the same thing, right? I'm going to go over friction first. And basically friction is really all around us, right? It's when two objects come in contact with one another. Again, it's a contact force, right? And when one rubs or slides against another object, right? And it's always going to slow an object down, right? Friction always. There's never a time where friction always helps accelerate it in a faster moving way. It's always going to accelerate it in the sense that it's going to always slow an object down. And that's because friction always goes in the opposite direction that the object is moving. So if an object is moving to the right, friction is always pushing against it. So it's going to go left in that case, right? And so we always think of friction as like, hey, when I rub my hands together, right, they get warmer. That's one thing that friction does. But it also, in our terms of talking about motion, it's always going to slow things down. All right. Now, I incorporated air resistance as part of this slide because air resistance is just a really a specific type of friction, and it's friction that's caused by air, right? So it's only air that can cause air resistance, right? Obviously, the name air resistance, but it's the same idea, right? It's basically when an object is moving in one direction, air is pushing against it, right? So it's always going to slow an object down as you go in. So when you see a parachute, right, you see the guy in the bird suit. These are all things that create air resistance to help the object slow down as it's moving through the air.